I need a proper What? I said shunt. Ask and you shall receive. Greetings, the Astro 30 here yet again, and I'm going to be looking at this flasher relay circuit one more time. I don't want to turn this into let's, reinvent the wheel channel. Now, I ordered this about a week ago, and I wrote that on here so we can see what value it is. It's 50 milliohm or 0.015 ohm. And they're a proper shunt. They're a copper and nickel composite, and they're designed as current shunts or current sense shunts in circuits. So what I want to do is I want to find out whether this shunt works in my flasher circuit. So let me get that set up and we'll have a look. There's the shunt there. It just barely fits in the breadboard sockets, but because it's a 1mm diameter shunt, but it fits in there. So I've got the desk lamp off because it just washes out the image sensor in my camera. So I'll turn the power supply on. Now currently I've got both of these globes connected together in parallel, and it's connected to ground here as well. So if I touch this to the output, we can see that it is actually flashing both globes normally, even though my hand's in the way, but you can see that there is a globe flashing there. So now if I disconnect one of the globes and only have now one, it flashes at double rate. Perfect. That's exactly what I wanted. And the thing is, I didn't have to mess with the comparison circuit too much, except where this pull-up resistor on pin 7 was, the 47K, which originally was a 1K, I was kind of interested to find out why it wouldn't work with a shunt that was less than 0.33 ohms. So I put a 0.22 in there yesterday, and then I decided to put a variable resistor, and I turned it down until the thing with both globes connected, because when both globes were connected it was flashing at double rate with that shunt. So I started turning the resistor down until it started flashing at the normal rate. And then when I disconnected the second globe it flashed at double rate. So then I measured the resistance and it was close to 1K. It was actually about 1.1K or something that I ended up turning it down to. And I thought, right, okay, well that's what it needs to be. It needs to be a 1K as it originally was. So I don't know why the circuit wasn't working properly when it was a 1K, and that transistor, which is on the second capacitor down here, was always turned on at 0.6 of a volt. I don't know why. And why it works properly now, I don't know. But that's good. I don't have to mess around with any resistor values. It will work perfectly fine with a 15 milliohm shunt as opposed to the 30 that was specified in the schematic originally. And I don't know if in the intro I said that the shunts I got were 50 milliohm. I meant 15 milliohm. But anyway. So okay, that's all well and good. So we know it works with a proper shunt. What would be a good idea to test now is going back to using a piece of copper wire as the shunt. Can we do it? Well, copper wire does actually have a certain amount of resistance per centimeter. So I'll just bring up a wire resistance calculator. Now its main unit of measure here is in meters, so that's 1000 millimeters. So I've calculated with a copper wire of a diameter of roughly 2 millimeters and a length of roughly 25 millimeters, we get close to 15 milliohms. We actually have 13 milliohms here, which is close to what the shunt is. So what I want to find out is if a piece of 25 millimeter length, 2 millimeter diameter copper wire, tinned, will work as a shunt. Now that I've fixed what the comparator was doing with the too high of a resistance there on the pull-up resistor. So if it does work, well then we've got two options now of how we can go about doing the shunt. And a short time later, there's my there. Can you stop doing that? I said shunt. Oh, bloody editors. Anyway, this will either work in the circuit or be a complete and utter fail. It's fashioned roughly the same width here as the other one, which is 15mm. It's a piece of 25mm long, close to 2mm thick wire that's been tinned, and I've just tacked on some 0.8mm tinned copper wire on the ends there, just so it can be plugged into the breadboard. So all I have to do is just remove this shunt without destroying it, and then put this one in its place. If I could see what I was doing, it'd be great, but I can't. Right, so it's not quite bent at the same width as the other one, but if I carefully maneuver stuff around, I can get it in there. Right, the shunt is in there. I don't think I've disturbed anything else, so the circuit should still work. Or not, whatever the case may be. So I'll just connect these bulbs back in parallel again. Turn the supply on. Interesting. Right, let's try it with one bulb. There you go. So there you go. The homemade shunt actually does work. So the reason why it wouldn't have worked the first time, and I had to have a really long piece of wire, was because of that pull-up resistor was too high. I shouldn't have messed with the circuit without thoroughly investigating how the circuit worked, which is what I did yesterday. And I came to the conclusion that I was wrong, which doesn't happen very often. Actually, no, yeah, it does. It happens all the time. So anyway, that aside, let's find out how hot that piece of wire gets with both globes connected, because there is going to be a significant amount of current going through the circuit. But I don't want to blow the globes. I can't really feel much heat at all. That seems fine to me. It's not even getting warm. I might drop that voltage back down to 12.8, which is normal battery voltage of a vehicle. And the circuit still appears to work. If I disconnect one of the globes, it flashes faster, as it should. So, excellent. Excellent. So we have two options here for this circuit. Either a proper shunt that's designed to be a precision resistance, or a piece of bloody tinned copper wire. Either will work. I don't think it has to be exactly, you know, that length. Although I was going to say I might want to try if I can put a 0.8mm length of wire there, but yeah, no. I should really probably calculate what that would be. So let's change the diameter to 0.8 of a millimeter. That puts our resistance to, interestingly, 83 milliohms. So yeah, 0.8 should still work. And if I was to change the length to, well, what the diameter of the, well, not the diameter, the length of the shunt actually is, which is not that, 0.15, we're more like 50 milliohms. So question, will a piece of this wire work as a shunt? Couldn't hurt to find out. Alright, as stupid as it sounds and looks, it is basically an experiment at this point. I've got the 0.8mm hookup wire, tin copper wire, whatever you want to call it, installed instead of the 2mm one. So I'll turn the supply back on. Well, apparently both globes are flashing at normal rate. Double rate. Huh. Well, how about that? and it doesn't appear to be getting that hot. I mean, this tin copper wire should be good up to at least 5-6 amps anyway. I only went with the thicker wire before because I wanted to make sure it would handle the current, you know. So we're currently at around about 50 milliohms with that piece of wire. Well, it's actually 20 millimeters long instead of 15 because of the bits that are bent over at the ends. So at 20 millimeter length, that's about 66 milliohms. So yeah, it'll work with basically any piece of wire. So I'll turn that off now because those globes are going to get pretty hot, and usually what they're installed in the reflector helps as a heatsink for it as well, and I don't have one. So we've got three options now: piece of tin copper wire, piece of copper wire which is like 2 millimeters in diameter roughly, or I think it's more like closer to 1.5, maybe 2, or a proper 15 milliohm shunt. So, alright, the next thing to do is I'm going to go through the changes to the schematic on the screen here for you. And this is going to be the finalised schematic, and then we'll look at one final thing before we close this video out. It's not really an exciting video, but it's exciting to me. Okay, and here's the finalised schematic. Not much has changed from the last one. Well, a little bit has. This resistor pull-up for pin 7 here has been changed back to its original 1K, and the circuit seems to work fine. The shunt has now moved over to this end of the schematic instead of where it was, which was here. It just made, you know, drawing this part of the comparator circuit a lot clearer. And the other change is I changed the 47K resistor that was on the stable oscillator from the previous one. I actually had a 4K7 connected to pin 7, then from pin 7 to pin 6 I had a 47K. I've now changed it to an stable oscillator using positive feedback from the output, so that eliminates one resistor. And I changed it to 33K because I found the flash rate was a little bit slow. It was like tick tock, which is a bit slow. So with this addition here, I've got some notes down here. Normal flash rate is approximately 213.8 milliseconds on and off at 2.3 hertz when both bulbs are connected. When a blown globe is detected, it's approximately 107.38 milliseconds on and off at 4.64 hertz, almost pretty much double the normal flash rate. Another note here: confirm the vehicle is negative ground, not positive, obviously. And I did measure the idle current when it's not actually doing anything, no bulbs connected or anything, and it's not flashing or oscillating. Our quiescent current is roughly 28 mA, which is on the high side, but that's fine. We'll also notice here we've got a 220 ohm resistor and a Zener diode, which is a 12 volt one. It's an 1N4742A, which is a 12 volt 1 watt Zener, which is then bypassed with this 10 microfarad tantalum capacitor. We also have another 10 microfarad tantalum capacitor on the end here. The reason why I'm using tantalum capacitors instead of electrolytics is for the reason I stated before. It's pretty hot underneath the dashboard, and it can get pretty cold underneath the dashboard. So we want the circuit to be as stable as possible and not change its flash rate at any point in time depending on the temperature. So, and the reason why I've got this Zener diode to bring this IC down to 12 volts is a pretty simple one, because the sit voltage, the average sit voltage of a battery in a car, which is what this is designed for, when the engine is off, is sitting between about 12.6 to 12.8 volt, 12.6 being on the lower side, and you probably should really check your charging system or battery. But 12.8 is about the nominal, and it can go up to anywhere close to 15 volts when the engine is running, when it's getting power off the alternator. It can be like 14.8 volts, and that's coming very close to the maximum voltage rating of this IC, which is 15 volts. So that's what that diode is there for, is to protect this IC and make sure that we're only feeding 12 volts into it, or just a slightly higher than 12 volts.
no more higher than 12.8 across the BCC line here. Now this comes after the relay, not before it. The relay isn't really that important as to whether it has 12 volts there or close to 15 volts. The relay will still operate fine, just so as will the light globes that are connected to the circuit. Other than that, nothing has changed. It's still the same circuit, and there's not much more else to say about it, except that it now works with either a piece of wire as a shunt or a proper 15 milliohm shunt. And doesn't have to be something convoluted like a 100 watt 0.33 ohm resistor, which I do have them still on order, and I have no idea when they're going to get here, because it's coming via Aramax Australia, and yeah, I've had pretty piss poor experiences with them before, and I also don't know what I'm going to do with them when I do get them. I suppose I'll find something to do with them. And just so everyone knows what wire resistance calculator I was using, it's this one, Omni Calculator. You can find it by searching it in Google, and it'll be the first result. The default length is in meters. Now, I've actually messed up the conversion here of 20 millimeters. This is actually 2 millimeters, because there's 1000 millimeters in a meter, so I should not have that many zeros. That's only 2 millimeters, and 2 millimeters at 0.8 millimeter diameter is 0.66. But if we actually change this to what the actual length is, well, our actual resistance is close to 0.668 milliohms. So it's, 0.6 of an ohm, which is okay. So that was my fault. You can change this to centimeters, so that'll be 2. The resistance is still the same. So if I put in what my original wire was, well, the resistance of that is more like 100 milliohms, which is fine. So we found out that the circuit will work at 0.015 ohms. We also found out it'll work at 0.1 of an ohm. And I had two 2-watt resistors, 0.22 across each other in parallel. That gave me 0.11, which is close to the same resistance as this. And the circuit works fine, except the resistors get hot, whereas the wire doesn't. And we've also found that at 0.8 of a millimeter, that the circuit will work quite happily, almost up to an ohm. So that's good to know. So yes, that was my mess up, but that's fine. So anyway, what do we do now with this circuit? Well, you know me, let's make a circuit board. And there we go there. It's a very sexily made circuit board. I'm using tantalum capacitors all the way throughout, except for the 10 nanofarad and the 100 nanofarad. I mean, I probably could use tantalum there as well, but yeah, they're more polarized capacitors, and you can get 0.1 microfarad tantalums, but as I said, they're polarized. Anyway, this is our dropper resistor and xenodiode circuit here for the 555 timer over here. And there's the smoothing capacitor or filter capacitor for that section. And most of the guts of the circuit are over here, and the comparator's over here. Now, yes, this is a fairly large board. I think it's about 66 millimeters something in length and about 38 high. Yeah, that's fine. Here's our shunt connection and our output transistor for the panel lights. Now, I made this so that it can actually be soldered in from the underside, put in the die-cast metal box, bent at right angles, and you put a screw through here into the die-cast box with a insulation washer set, and you've got a heatsink. Now, this transistor won't require that much of a substantial heatsink because it's only going to be, supplying a current of roughly 300 milliamps maximum, maybe 400. It depends on the globes used inside the panel. And I don't actually have a car to test this on, to rip into its wiring. Most cars now are electronic flashes, and they don't use the panel light section like they used to. They just have the panel lights going off each side of the flasher bulbs. So the left arrow is connected to the left set of flashing bulbs on the outside of the vehicle, and the right arrow is connected to the right side, respectively. Some cars do use a dual flasher, that is, they have 2 flasher units, one for the left, one for the right, but they're fairly rare now. They mostly have one relay flasher for the normal indicator and probably a separate one for the hazards, because with this panel light arrangement, the hazard flasher is not going to work, and it won't flash the hazard lights or the arrow lights on the dashboard when the hazards are on because of the way that it's configured. So I don't believe that those cars that had a panel connection actually had a hazard light switch. If they did, they would have had to have switched out the globes in the panel and disconnected them from the outside globes and actually grounded them instead. I don't know. Anyway, that's irrelevant. That's getting off topic. So this will be something I will have sent off for manufacture soon. I've tested the circuit as best as I can, and as far as I want to test it, it works. We'll just have a quick look at the bottom, because we like bottoms on this channel. Well, I do anyway. Now, I've made it clear that it's not suitable for 24 volt systems because, well, you blow it up, and it's negative chassis vehicles only. We'll notice that we've got bare copper, which will be tinned in the end, here and here and here. That's so that the copper can handle the maximum amount of current when it's tinned. Because it's had solder mask on it, the current capability will be a lot lower. So with the tin copper wire sections here, and roughly around about 25 millimeters in total length, you can handle up to at least 7 amps of current continuously through those wires. However, it won't be 7 amps continuous because it's oscillating on and off, on and off. So there's going to be a break in between, so it's not going to have, in this case, 4 amps going through the circuit all the time. So that's something I'm going to experiment. I've never actually done a circuit board like this. But yeah, that's the flasher relay. It is on the large side. Oh, and this Xenon diode is not dropping the supply for this LM393 either, because this IC can handle up to 30 volt DC just fine. So the final thing we'll look at before I close this video out is the specs on this particular relay, which I've got sitting on the desk. So I'll just bring its data sheet up. So I found the relay on RS Components, and they say it's a 5 amp switching current, which is not what I read in the data sheet. But it's only available for back order, so it's kind of getting obsolete now. And so this is the data sheet for it. Now, it does say down here the contact material, normal switching capacity, is 10 amps at 250 volt AC, 10 amps at 125 volt AC, and 6 amps at 277 volt AC, which is interesting that it's different between that and, well, yeah, that's higher than 250 volt. Okay, so that's what the switching current is up to 10 amps, so RS is wrong. If my computer would hurry up. Now let's see what the actual coil voltage requirements are. So here we go. Here's the JS1 12 volt F as I've specified, which is sealed type 1 form C. Nominal coil voltage is 12 volts. Pickup is 8.4, so that's the minimum voltage that it can run at. Dropout voltage is 1.2. And it doesn't actually have a maximum voltage, which is interesting. But the nominal current draw of that is 30 mA. So yeah, it doesn't actually say what the maximum coil voltage is, but I'm pretty sure it will handle up to 16 just fine, and there's its pinouts. Now, Ultronics do sell a similar relay to this. So I'll just bring that up. So this is basically the replacement relay, same form factor for the JS1-12 volt-F. So this is probably what I'll change the silk screen to, whatever the part number of this is. So as we can see that the measurements are going to be exactly the same as the Panasonic relay. It's 12.2 between the coil pin and one of the contact pins, and the center is offset by about 2.1 millimeters, so that makes it 14.3 between here and here, which is right, and the outside dimensions are roughly the same, if not a little bit smaller. So there is their specifications there. Maximum voltage at AC switching is 380 volt, which is better than the 270 of the Panasonic. Maximum switching current AC is 10 amps and DC is also 10 amps. And the coil resistance is 400 ohm. And there's nothing else there. There's the dimensions. It's actually slightly smaller than my footprint, which is good. So here's the data sheet for that particular relay. It's an NT73-2, and there's the, what's printed on the relay as to what the ordering information is. Anyway, that's not what we're interested in. So let's have a look for the maximum parameters of the coil. Right, so here we go. With the dash numbers like this, if we're choosing a 12 volt relay, and they're the same on all three parts of the rows here, for a 12 volt relay, the maximum voltage that you put across that coil is 15.6. There you go. Coil resistance is 400 ohms, and it's 0.36 watts power consumption through the coil, but it doesn't give me the current. I mean, I could calculate the wattage back to current. According to this picture, NT73-2C-10. There we go. It's an NT73-2C-10. So that information there is interesting. So 1 is the part number, which is NT732. Contact arrangement is C in this case, so that's 1C. 3 is the enclosure type, sealed type for S. And 4 is the contact rating. So that number 10 in the picture on Ultronics there means it's 10 amp contacts. So there are other numbers which are probably further down on the relay which you can't see. It just says DC 12 volts, so that's what its coil voltage is. And 0.36 is the coil's consumption. So I reckon that's around about 36 milliamps or something. So anyway, that's what I've got with that. So I'll change the schematic around to use the NT73-2 relay rather than what I've got, because that relay looks like it's becoming obsolete. Anyway, I don't want this video to go on too much longer about me talking about random stuff. So I'm going to leave this video here. If you enjoyed it, please remember to go down below and comment and subscribe if you haven't done so already. And I will be at some point having the PCB manufactured, but that'll be in the future. But I actually don't have a real use for this particular circuit at the moment, but I may do. Don't know. I'm still going to build it anyway. Anyway, this is Joshua Thoya saying, see ya. Thank you for watching. Have a great day.